talk is about distributed exact weighted all pairs shortest passing for tilde of n to power of 4 rounds, and Paul Saramorak will present.
Hi, I'm Tachapon Saranurak, and this talk is about distributed algorithm, but in a different model. This is in congest model, not local like the last talk. So let me tell you about this model. So you have a distributed network, and you just think of it as a graph of n nodes, and you have the diameter of the graph d. So in this case, the node is n is 4 and d is 2. So diameter is just the maximum number of hops to get from any node to any node. Okay. And the point of the model is that each node only knows their neighbors. For example, here the node 4 only knows that it is connected to 2 and 3, but it has no idea whether 2 and 3 are connected. Okay? So this is why it is local, but okay, and in this model, usually we just want the network to compute its own properties. And there is a notion of time complexity, which is different from the local model. In this congest model, we think that we have a number of days, we have day and night, and on each day, each node can exchange only one bit to each other, actually log n bit, but you think of it as one bit. Okay? And on each night, each node can perform any local computation, can be NP complete problem, anything. And the next day it exchange another bit. And the night it perform the local computation and so on. So if that computation finished in t days, then we just say that the time complexity for that problem is t. So now let me tell you one example of the problem that can be solved quite easy in this model. It's just single source shortest path problem. So basically I will tell you how to do breadth first search in this model. So let's see. So in this problem, you have that for each node want to know the distance from itself, from S to itself. In the beginning, they have no idea what the distance is, and then at day 1, the source just tell the neighbors the distance, and the neighbor get the distance, and at night, the blue node, which is 2 and 3, just update the distance of itself. And the next day, those that is updated just again tell the distance and so on. At night, the blue node that get the distance just update. Okay. And this just go on. And it is quite easy to see that this algorithm should be finished in diameter time. So this is one problem that can be solved quite easy. But in our talk, we will look at a more complicated problem, which is all pair, shortest path, and inverted graph. So in this problem, we want to solve, the goal is the following. We want that each node it should know distance from every node to itself. For example, 2 want to know the distance from 1, 3, and 4. Okay, so that's one difference. Another difference is that there is some weight on each edge, can be large. And so because of these two different, there are two difficulties that seems like this problem should be hard. Because if you just run a best first search, it might take W time, which is W is max weight. And this can be really large. And another one is that if you just run BFS from n node, then it might take a lot of time. But so this is quite challenging, but people have tried to do this. So let's see the progress of this problem. So this problem is solved kind of completely in unweighted case. So the people have get the lower bound first of n, and then there is an upper bound of n. So in unweighted case, this is completely solved. But for weighted case, like so far we don't know like the non-trivial algorithm. We just know that okay, everyone just broadcasts everything they know, and that's it. And that takes n square time, and we get stuck. So people shift the focus to just approximation version, and in this case, there are two works by Lenzen and Pratchamian and Danupon Nanongkai also get. We have this almost tight bound of n, and they get a 1 plus epsilon approximation. So this is kind of solved. Just want to point out about this field a bit that in this congest model, there are actually many other impressive developments for other approximation algorithms. There are nearly tight bound for other problems like not just all-pair shortest path, but other graph problems. And there are many cool techniques from lower bound and upper bound. But because we kind of have some good knowledge on approximation version of many problems, the focus shifts back to exact problem. And just recently, Elkin in the last talk managed to break the bound from n square to something less than n square. And in this talk, basically, we show that this can be done even faster. It can be done in n to the 1.25. And actually, our work are independent from Elkin, but basically the two works are like the first two works that break this n square bound. And another thing is that we have other result, which is k-source shortest path. I won't define it, but basically instead of we want distance from every node, we just want the distance from just k sources. The bottom line of this work is just saying that when the number of sources is quite large, not too small, then our work is like the fastest. So there are 3 technical contributions of this work. The first one is scaling technique. So the scaling technique is the following. Suppose you have a graph and the maximum weight of any edge is W. So scaling technique is basically a reduction from weighted instance that can have high weight to log W instances with simpler weight. Okay. The really high level idea is just that like at the ith iteration you can kind of solve the ith bit of the weight. Okay. But and this kind of high level idea is used in many centralized algorithms, MaxFlow, shortest path, maximum matching. The point is that this work is just the first. This is the first work that uses scaling technique for distributed shortest path. So in particular, we have that we use this scaling technique, and we will need to solve problem in just logarithmic iteration. And the first iteration we have a very simple weight, like 0, 1 weight on each edge. And for other iteration, it becomes more complicated, but we can manage it. we have something like weighted diameter is n. This is implied by if you have that, it is 0, 1 weight, but we don't really have that. But this is what we really need actually. But there are something which is much more complicated, like it is actually directed, and there are n different weight functions, but don't worry, all the technique that we show actually can handle all of these bad things. But from now, you just think that the weight is just 0, 1, just for simplicity. And the next black box that we show is something called short range algorithm. So in this setting, this is a useful black box that we will use. So consider the problem which is like a restricted problem of APSP, which is called H-hop APSP. So the goal here is such that every node S should know the distance to T only if the number of hops from S to T is bounded by H. Okay. If H is n, then let me tell you, the number of hops is the number of edges from in the shortest path from S to T. And if H is n here, then this problem is just APSP problem. But here H can be smaller. And so in this problem, if you just use Bell-Manford, you can make it like in NH rounds. And the point here is that we can speed it up to n root h round if the graph has simple weight like 0, 1. And actually we have something more complicated, and actually even more complicated we can handle it. The nice thing to know is that this technique alone actually already gives us n to the 1.5 algorithm, which is faster than Elkin's. So let me tell you really briefly in high level how do we do this. So here we have that the weight are non-positive, non-negative. It can be 0 up to anything, and but the weight the negative the weighted diameter is n. What is hard about this problem is actually only because of these 0 weight edges. It becomes difficult because suppose that you don't have this 0 weight, then you can solve this using kind of standard technique in n time. So the point of the algorithm is to handle these 0 weight edges. And basically the algorithm just changed this 0 weight to something like very small, but non-zero. And then just use this standard technique, which is BFS plus random delay. And the running time basically just this times root h, because the time we just run this thing with a more fine-grained time scale. The point is that once you do this, then you kind of just already solve the problem, but with some additive error of root h. And after that, you can fix this by running Bell-Manford with root h round, and you are done. So this is one black box. Another one that is kind of nice is the following. Suppose you have R sync, and in the beginning, for every node V and sync T, the node V know the distance from itself to T. And the goal here is to just reverse the knowledge. We want that instead of V knows this thing, we want the sync to know it. This is what we need to do. And there is a trivial algorithm again to do this in NR time, just by broadcasting everything. And what we can show is Okay, we can speed it up to n root r time. And again, a really high-level idea. We can show that there are not many nodes, just root r node, such that it makes everything. It makes the broadcasting algorithm slow. And we just deal with this node like separately, and then for the rest it becomes fast. So this now I just let's see how these black box like fit together. So there is one standard thing which is called center. So now that I want to define to you. So suppose now you have a graph with 0-1 weighted 0-1 weight that we get from scaling technique. And it's actually more complicated, but okay. Anyway, here the center is you just sample each node with probability 1 over root n. And then you get some node, the square one, which I call the center. And once we have this, there is a standard argument which show the following. So consider any shortest path P from S to T. With standard argument, we can show that either the number of edges, the hop from S to T is just at most root n, or there exists the center which is close to S, and also another one which is close to C, just root n hop. So this we will exploit. And now there are 4 main steps of the algorithm. So we call that the goal here is that we want T to know the length from S to T of the length of this path. Okay. The first step toward this goal is that in the first step we will have that S will know the distance to the center nearest it. And this will be done by, because the number of hops here will be short, this will be done by our black box, which is short range algorithm. And next, S will know the distance from S to the center near T. This will be easy, and I will not explain this. And then next is that we want to reverse the knowledge. Instead of here S know the distance, now we want this center near T to know the distance, the same distance here. Okay, so this just reverse the knowledge, and then the last step is we want that we want to propagate the information from the center near T to T. And this can be done again using something, a modified algorithm of the short range. So this is a really high level, but let me just go through it a bit. Why we get our running time. So look at the first step here, because here the number of hops is root n. Okay, so that's why we get running time here n root h, which is n to the 1 to the 5 over 4. And in the next step, this can be done by we just let the center broadcasting some information. Is kind of easy, and we are done in actually n time. And in this step, to get this, we just set the center to be sync. And now the knowledge, this is exactly the situation that we want. We want to reverse the knowledge between node and the center. And because of this, we get that the center know the distance. So we get this running time again. And the last step also we are done by just modifying something. So the point, so just let me conclude. The result here, basically we just show that this exact weighted NPSP algorithm can be done in n to the 1.25 rounds. We break this trivial n square bounds, and it kind of gives us hope to get linear time algorithm. And there are 3 technical contributions. First, we use scaling technique in this setting. Second, we show a non-trivial algorithm for short range. Instead of NH, it becomes N root H. And we show a non-trivial algorithm for reversing the knowledge. So, open problem. It would be really interesting to have the separation between exact problem and approximation problem. Can we have any lower bound for that distinguish this? And I think because now the field kind of have a good knowledge on approximation problem, can we get better bound for exact problem as well? Yes. So that concludes my talk. Thanks.
Questions?
Yes.
So what's the total running time, including the work done on each node at the map? And how do these algorithms compare, because if you want only 1 plus epsilon, you said that you can do in OOP.
Yes.
So is the work done very significantly different, or?
So you asked about local computation inside
Yes.
each node. So I haven't thought about this, but it shouldn't be. It shouldn't be complicated at all inside each node. Yeah.
Okay.
Yeah. Sorry. Yeah.
Any other question? Let's say the speaker again.
Okay.